Today's goal is to find all zeros meaning roots or x-intercepts, of a polynomial. Again, these are the types of functions that are cubic, quadratic, degree 7, degree 142, something like that, and express the polynomial. So we're going to rewrite polynomials in fully factored form. Recall that a polynomial is in fully factored form if it's written as the product, or you're multiplying a whole bunch of linear factors. So it should look something like f of x is x plus 3 times x minus 2. Maybe there are more linear factors like 2x plus 5, or even x, which is just x minus 0. Or maybe x minus 2 is even squared, because that just means x minus 2 times x minus 2. A non-example of fully factored form would be something like g of x is x squared minus 3x times x squared minus 1, because you've got these quadratic factors. So you'd have to keep factoring it. It would look like x times x minus 3. I'm taking what they have in common out, times x plus 1, x minus 1. I'm just factoring this difference of perfect squares. Now this would be fully factored because every one of these factors is linear. It's in the form mx plus b. Okay. One way to tell if a function is fully factored is to look at every single factor and make sure they're linear. Another way to tell if a function is fully factored is to apply the fundamental theorem of algebra. Fundamental meaning it's absolutely critical, groundbreaking. And the fundamental theorem of algebra states that a degree n polynomial always has n roots. And if it has n roots, then it has n factors. So for example, this guy up top, we've got x to the first, x to the first. We've got x being squared, 2x to the first. So if we multiplied all these terms with x out, we would have 1x times 1x times 1x times 1x times 2x. So 1, 2, 3, 4, 5. We'd end up with 2x to the fifth. So since this is a degree 5 polynomial, it should end up with 5 linear factors. Oh yeah, there's 1, 2, 3, 4. Right? It's multiplicity 2, so it counts as 2 different factors, 5. Yeah, there are 5 linear factors. So there would be 5 roots. You get 0, -3, 2, and 2. It's a multiplicity 2, so the root 2 counts twice, and -5 halves. So that's the fundamental theorem of algebra. We'll use it today. Take a look at our first example. Completely factor this function. I see that it's cubic, so I expect when I am completely factored, there should be 3 roots and 3 factors. Given that f of -6 is 0, here's a hint. It's saying if you put the x value -6 into the function, you get out the y value 0. So -6 has to be one of our roots. If -6 is a root, that'll help us because I don't actually know how to factor using the big X. I could try taking an x out of these terms, but I don't know, do they have something in common? I'm not really sure. So if I can't factor by grouping and I can't factor using the big X strategy, I'll have to use synthetic division to break it down a little bit and see if I can go from there. So -6 has to be our root. Let's write out the coefficients of our function. Drop some space and divide. Oh, good. We were right. -6 is a factor. So we can take this function f of x, and we can factor it into x plus 6. This is because -6 is the root that corresponds to the factor x plus 6 times, here are our leftovers. Here's the constant, the number by itself, coefficient of x squared. So our leftovers would be 1x squared minus 10x plus 29. Well, we've rewritten the function with 2 factors, but it's cubic degree 3, so it's not fully factored. Well, that makes sense because we've got an x squared term here, so we'll have to keep factoring. Now, this is quadratic inside of this set of parentheses. So let's try our big X method, 2 numbers that multiply to 29 and add up to -10. It can't be done, so we'll have to use the quadratic formula. Just on this blue factor, the quadratic bit. So we have 10 plus or minus the square root of 100 minus 4 times 1 times 29 is 116 all over 2. And so we get x is 10 plus or minus square root of negative 16 all over 2. That would be 10 plus or minus square root of 16 square root of negative 1. We're taking the square root of negative 1 out because the square root of negative 1 is I. So this would be x is 5, 10 over 2, plus or minus 2i, 4i over 2. So even though this is going to look weird, we can take this quadratic factor and break it into x minus. These are my two roots. They're complex, but they're roots nonetheless. You wouldn't see them as x-intercepts on the graph, but they are roots. So we can write our function f of x as x plus 6. We figured that factor out long ago. And then we'll break down this quadratic factor into x minus 5 plus 2i and x minus 5 minus 2i. It looks a little cumbersome, but this is the function in fully factored form because these factors are all linear. They all have x with the exponent 1. Okay, let's take a look at another example. And this will be our last example today. Find all the zeros. Finding all the zeros means we have to get it fully factored and then set those factors equal to 0. Here's our hint. Part of the graph is shown below. We can see that it's been cut off here and here, so we're not sure exactly what's happening, but this hint is good enough. We can see it looks like we have a 0 at negative 1. Again, I don't know how to factor this because it's not quadratic, and it can't be factored by grouping. 5x and 14 have nothing in common, so I can divide out by the factor x plus 1, knowing that negative 1 is a root. So let's go ahead and divide. So that means that f of x, our original function, will look like x plus 1. That's the factor associated with this root, times x squared minus 9x plus 14. Oh, this is nice. It's not fully factored because it's quadratic, not linear. But I can use the big X, two numbers that multiply to 14 and add up to negative 9. Those are easy to find. So we can just break it down further into x plus 1 times x minus 7 times the quantity x minus 2. Now we're not done because our goal is to find the zeros, the roots. And we know if it's a root that the y value is 0. So we'll have 0 equals x plus 1 times x minus 7 times x minus 2. That looks like, right now, something times something else, this time multiplied by a third factor multiplied to 0. The only way to get 0 through multiplication is if one of these things is 0. So either x plus 1 must be 0, or x minus 7 must be 0, or x minus 2. One of these guys has to be 0, because 0 times anything will give you this final product of 0. So x is either negative 1, 7, or positive 2. That means my function has roots at negative 1, 0, and 7, 0, and 2, 0. It makes sense that we're done here because we were given a cubic function, and we know that cubic functions will always have 3 roots corresponding to 3 factors.